Good afternoon, everyone, or maybe I should say good evening. Welcome to another installment of the Parsippany Green Team. Today, our presenter is Matthew Cavanaugh, and he's going to talk to us about energy storage systems. Matthew, welcome and take it away.
All right, thank you, Jean. All right, so this is series number 19 in an education series that we've been leading. Thank you to the library for hosting this. This specific topic is on energy storage systems, and we're presenting this as the Parsippany Green Team. My name is Matt Cavanaugh. I'm the co-leader of the Parsippany Green Team. And if you aren't aware of our mission, the mission of the Green Team is to collaborate with our residents, town government, and business community to identify and implement programs that improve our quality of life and the physical, environmental, and financial sustainability of our community. So energy storage systems is one of the topics we're going to cover, and I'll get into the topic here. So in terms of the agenda, first I'll cover energy storage systems at a glance. I'll get into the types of energy storage systems, look at the cost versus capacity and energy storage systems and what that means for the future grid, and then get a little bit more in detail into the various types: electrochemical, mechanical, and thermodynamic energy storage systems. The first thing, plug for the Green Team. Our goal is to pursue certification in the Sustainable Jersey program. Sustainable Jersey is a points-based, action-based nonprofit in New Jersey that helps towns implement sustainable solutions across the town. And so far, our goal this year was to submit bronze worth 150 points. As of June, we have submitted this, and we're awaiting certification points to see if we got that. And next year, we're shooting for silver. And then in 2023, we're also shooting for the gold certification in energy. So this specific topic facilitates the discussion around gold and energy, which is all about carbon reduction. And if you aren't aware, there's 18 broad categories across Sustainable Jersey, from animals to food to energy to natural resources, land use. You can see the breadth of and extent of sustainable solutions. So actions within each of these categories, the Green Team is selecting these and then pursuing them across the town and working with the municipal government to earn the points and get the actions completed. So there's something for everybody, and I encourage you to participate if it's of interest to you. So getting into renewable energy storage systems, the storage systems really complement the growth of renewable energy and electric vehicles in the future that we have. So one of the challenges with renewable energy is that there's an intermittency problem, meaning that when the sun doesn't shine, the solar doesn't work. When the wind isn't blowing, the wind turbines don't work, and you're not generating electricity. But you still need energy all the time. You need power, you need energy. So the solution is to store it for later use. And there's an incredible spectrum of energy storage options available. You can see the chart down here with hydrogen, pumped hydro, redox, lead acid battery, flywheels, capacitors, supercoils, everything across electrical, mechanical, chemical, and gravity systems. So we're going to get into those a little bit more detail and talk through some of the solutions, the maturity curves, and the plus and minuses of some of the applications. So types, energy storage technologies span these four main categories: electrochemical, electromagnetic, thermodynamic, and mechanical. Inside of electrochemical includes batteries, flow batteries, and hydrogen. Inside electromagnetic is capacitors and magnetic field energy storage systems. Thermodynamic solutions include compressed air energy storage and pressure and heat systems, including thermoelectric heat transfers. And then finally, mechanical includes gravity or potential energy storage systems, and then kinetic energy, such as flywheels. And the interesting thing about this spectrum is that it follows the first law of thermodynamics, which is energy can neither be created nor destroyed during a process. It can only change forms. And there's always conservation of energy, meaning that one energy transfers into another, for example, from electrical to potential or chemical into electrical. All of these energy spectrums can be converted from one to the other back and forth. And that's why there's such a broad spectrum of solutions available. And I'm going to get into some of these. But the trade-offs exist for various types, and there are also different use cases based on how big you need the storage to be, how much power you need, how much available space you have, or the application that you're trying to use it for. So the cost versus capacity curve for energy is a huge aspect of how these technologies fall out. So energy storage solution technologies are competing in different applications like electric vehicles, grid support, other applications. And there's a learning curve tied to the unit of energy cost and also the unit of power cost. And one of the big considerations is how much energy do you need? How much power do you need at any given moment? And that in turn gets paired with the required application that you might need. So you can see here, this is a cost versus power or power versus energy curve for different solutions. The different technologies are rated in here based on the cost per unit power. So this is dollars per kilowatt. And then the cost per unit energy, dollars per kilowatt hour. So as you come down into the lower left-hand side here, it's better for power applications and better for energy management systems. And you can see different applications fall in this curve. And this is what drives the usability of these applications. So for example, compressed air is definitely low on a dollar per kilowatt hour. And it's also has cost per unit power is also very low. So this is a highly competitive energy solution. And then the duration versus capacity. So how long do you need the energy that you're going to pull from the energy system? That's a really big, important question. And the different technologies that are available fall on a spectrum of duration. So this is the discharge time at rated power. How long can you support a power function from the energy storage system? And then also, how big is the energy storage on a kilowatt hour, megawatt hour, gigawatt hour system? And the technologies range in size because of physical limitations based on the different technologies. So you can see up here, pumped hydropower, which I'll get into, has long duration, can support applications up to a day, and then it can store up to 100 gigawatt hours of energy in the pumped hydropower system. Compressed air systems, CAES, are also very powerful and long duration. And then some of the more theoretical ones are in these chemical applications, which are futuristic, really. So one of the applications of energy storage, as I mentioned with renewable energy, is to support the distributed energy grid of the future. And right now, grid networks primarily consist of centralized power plants, pumping out power, pumping out electricity across long distribution lines to get to the final customer. So if you can see this schematic here, it goes from a power generations power plant up to a 400 kilovolt power lines, through a transformer to a 275 kilovolt power lines, down to another transformer, 132 kilovolt voltage. Then it steps down again and again to get to 240 volts or 120 volts in your power outlet at your house. So there's a lot of infrastructure required for this. And the grid of the future is going to be more distributed from the standpoint of energy, from energy availability, and it's going to look a lot different than it will today in terms of this hub and spoke model. So it's going to be distributed, meaning power will be available where it's being used, whether from solar or wind or energy storage. The power will be closer to the point of consumption, and it will be a much more integrated network between cars, solutions, and then finally energy storage. So the modernized grid is going to be a key priority as renewable energy increases. And again, solving for the intermittency problem is going to be important as renewable energy penetrates the grid more. So that being said, I'm going to get into electrochemical batteries. So this includes batteries, flow batteries, and hydrogen batteries, hydrogen fuel cells. So these applications are really good for mobile and stationary applications. The improvement of the power density and the cost has been really good over time. And the power density and the cost really drive the application curve. So you can see, for example, in 2010 here, it cost $1,200 per kilowatt hour for a lithium ion battery. And this has dropped precipitously down to a range below in the 250s. And then futuristically, it's expected to get in the $100 range by 2030. This is an estimate. And coincidentally, this corresponds to the growth of electric vehicles, which need lithium ion batteries and primarily use those. So the continuous fall of cost is really important as these applications come online. But then additionally, the continuous improvement in power density is going to be important for new technologies. So one of the reasons lithium ion is so useful is because it's very light compared to lead acid and nickel cadmium, and it has a very high power density. So this is a curve here you can see of watt hours per liter and comparing watt hours per kilogram. So this is weight versus volume on a schematic. And you can see where the different battery technologies fall onto this range. So improving battery technology is going to be really important for this electrochemical penetration. And it's not totally sure exactly which paradigm will finally play out, but there is a lot of technologies that are theoretical and are on this curve of development where, you know, we'll see over time which technology actually plays out and becomes the dominant one. But right now, lithium ion batteries are in the lead, and they're being used for both stationary power energy storage systems and electric vehicles at the same time. So another electrochemical battery energy storage system is a flow battery and hydrogen fuel cells. So I've listed a couple schematics here of the two different versions. So interestingly, a flow battery is similar to a lithium ion battery in that there's a positive and a negative, and except that the tanks that contain the positive and the negative fluids can be as large as they need to be to facilitate the power capacity that you have. So this is really good for large scale applications, not necessarily mobile applications, but the fluids correspond and interact with each other to transfer the power back and forth through a medium, and then drive a power source or a load from there. And then hydrogen fuel cell batteries is based on the premise of hydrogen and an oxidant passing through an anode and a cathode to create electricity and move the ions of electricity back and forth. And one of the interesting things about hydrogen is that it can be produced from electrolysis of water, where electricity can be ran through water solution to create hydrogen gas and oxygen. So it splits the molecule into hydrogen gas and oxygen. And the renewable energy can be used to create this electrolysis solution, thereby creating 100% green hydrogen for use in hydrogen fuel cells or compressed hydrogen for technologies such as transportation. So another electrochemical use here is the flow batteries and hydrogen. This is a growing applications, and I'll get into the penetration a little bit later. But basically, these are really interesting technologies. One thing I wanted to mention about these technologies is it facilitates a infrastructure that's similar to how we kind of think about our gasoline and our petroleum infrastructure right now, where you can have a working fluid that has energy contained in it that can be transferred to something rather quickly in a refueling type situation, and then you could move along with some mobile application or a transportation solution. So it potentially could backfill some of the existing methodology that we have now. Energy storage systems. So this is gravity and kinetic energy. So solutions across this spectrum include pumped hydropower, flywheel, which is kinetic, and then potential energy systems. So potential energy systems is primarily the dominant technology is called pumped hydropower. And this is based on the premise that if you take a working fluid in a lower reservoir and you use energy to pump it up to a higher elevation, as you increase the elevation, you're increasing the potential energy of that fluid, which is stored energy in the system. And that energy can be extracted in the flow and running the fluid back down through a motor or generator to recapture a lot of the energy. Some of these are as about 90% efficient. So that means that 90% of the energy that you pump up to this upper reservoir can be used for future applications on the way down. So here's a couple pictures of large pump hydropower stations. So these can be man-made or they could be potentially natural features. But the dominant form of energy storage is pumped hydropower. And this is also the largest duration and largest capacity in terms of the field. So another gravity system, these are type of things that are theoretical and are coming online in terms of technology. But for example, this solution builds a tower out of cinder blocks. So as you pull the cinder block up and put it back into place, you're increasing the potential energy of the cinder block. And then when you bring it back down, you can run that through a generator and extract the energy in the reverse mode. So this is really interesting. This could facilitate renewable energy as well, where you can store energy indefinitely, meaning that as long as the cinder block does not degrade, then essentially you have the energy stored in these concrete towers for use later on. They're also looking at applications where you're using railways and moving heavy bodies of material uphill on a railway to store the energy. Again, this is potential energy. You're pushing it up a hill, you're storing potential energy, and then that can be extracted on the way down. But large scale applications, would include things that could be buried in mine shafts or large heavy capacitance that could be pumped or moved up and down to store the energy and then also extract it back down when you lower the weight back down. So gravity systems are really interesting because they hold the potential for long duration energy storage, which does not degrade and isn't as affected by degradation over time. Thermodynamic or heat applications. So the principle of these energy storage systems is working on the materials and heat exchange. So properties of materials, how much heat can they take into the material, and the phase change and latent heat are the dominant systems here. So if you remember, your chemistry, as you increase energy into a material, it will transform from a gas, to a solid, to a liquid, to a gas. And the latent heat in this phase change process can be used and stored for future use in a medium of some kind. And that's how the thermodynamic energy storage systems really work. Another is for example, is a concentrated solar power plant. And in this one, there's mirrors that concentrate the sunshine on a central location to heat up a working fluid, which then goes into thermal storage tanks and can be moved into the generation system to extract that for later use and use it as a working fluid, just like a steam turbine. And these are interesting technologies. They take up a lot of land area, but there's different applications for thermodynamic heat exchange systems. You can also think of this as, here's an example of an ice battery. So as you extract heat from water, it will turn to ice. That heat can be stored for then later use and then pumped back into the working fluid to essentially store it again and reverse that back and forth. Ground source heat pumps and geothermal systems operate on this principle as well, where you're moving thermal energy in and out of the ground and using that for future use to run power cycles. Compressed air is also a thermodynamic energy storage systems. Now, the principle here is taking advantage of the pressure differentials for a gas media. And this typically will require large storage basins like salt caverns, depleted gas reservoirs, or old mines. But essentially, in this case, electricity is used to run a compressor. That compressor pressurizes the gas and pumps it down into the reservoir and continues to pressurize that gas. And when you run that back through an expansion valve on the other side, you can run a generator and produce electricity, which can then be used for the grid. So this is also a technology that's on the larger duration side, that's on the larger scale side. And you can take this and use it with existing features that you might already have to facilitate this technology. Depleted gas reservoirs could also be used, and the duration can be very long for these storage applications. And then I wanted to get into specifically end of life for batteries, because a lot of people are concerned about what happens to all the batteries that we're going to use in the future for the grid. And the idea would be to have a circular economy around the batteries. So taking everything in that battery and reusing it in a circular way to extract plastics, binders, take away all the leaching, and get the iron, copper, precious metals such as aluminum and graphite back into a system that could be used to produce new batteries. And this is an alternative that oil cannot produce. Once the oil is burned, the carbon is in the atmosphere, and with a battery solution, you have the ability to potentially reuse all the materials again and again and again, and stop extracting raw materials from the planet. And then I wanted to get into, some of the technologies from a capacity standpoint. So I mentioned that pumped hydropower takes up the lion's share of the energy storage in the US. In this case, it's 94% or 25.2 gigawatts. The other 6% is the growing technologies such as thermal storage and batteries, compressed air, and flywheels. And you can see here on the right-hand side, the growing trend in these technologies, primarily driven by lithium-ion batteries and then new thermal technologies as well. So in short, there are a lot of different medium and solutions for storage of electricity and energy that can be used to facilitate the grid of the future and facilitate more renewable energy penetration into the grid. And it's a really exciting time as these technologies come to maturity. And basically, these technologies can facilitate resiliency features as well, where when the power goes out, we can keep the electricity on also. So Jean, that's the last slide I had. And I wanted to leave some time open for questions if anyone had any.
I was wondering if there's something in the future for people who live who get a lot of sunlight, and I'm not talking about the solar panels that you put on the roof, but if you live in a condo with a balcony that gets a lot of sunlight, are there any is there anything out there that would something small scale that would convert that sunlight into energy I could use around the home, if it's even to power my computer or my cell phone, and any little thing helps.
So they make small portable solar energy systems with smaller solar panels that can be mounted in pretty much anywhere and then ran back into a battery that could produce AC electrical power or DC power for your cell phones. So some of these are considered like off-grid solar kits that you could use, put the solar panel in the sun and it will charge up the battery and run and basically allow DC to AC conversion for your laptop or another electrical appliance. So they do make small kits like that don't take up a whole lot of size, that you can put up and take really easy. You can move them around. They're portable. And in your application where you have a balcony and a little bit of sunlight, that could be a solution.
I had one more question, just I guess a general knowledge question. Is a battery considered a fire hazard? So if you have energy that you've stored in the battery and it's lying around, are there certain things that you should keep in mind, like don't expose it to too much sun, I don't know, heat, or keep it in the shade? I don't know. Again, sort of coming into this very uninformed, is fire, the danger of fire an issue?
A lot of batteries have a working range in terms of temperature and also modulate the amount of energy that can be flowed into the battery in a time frame, so to protect the safety features of the battery. With a battery, what you're worried about is overheating. So, extreme heats above 100 degrees, you should try and keep the batteries in a cooler climate, somewhere between, 90 to 50 degrees or so. Just like any battery, it degrades in terms of its potential as the temperature increases. But the features of the battery are designed to keep it safe under working conditions.